Today we're going to be talking about a different kind of syntactic analysis using constituency grammars. First, why are we using constituency grammars? A central question in linguistics is how do we know when a sentence is grammatical? And historically, one of the first ways that people reasoned about this question was using a hierarchical universal structure called parse trees. Today we're going to be talking about this formalization, how we can learn this from data, and then apply it to sentences. And this formalization is called context-free grammar. A context-free grammar is defined as a set of 4 elements. These elements are first, a set of non-terminal symbols that correspond to latent syntactic structures such as noun phrases or verb phrases that we don't actually see in a written sentence, but we believe to be there. And these are often multi-word syntactic abstractions. The second element are sets of terminal symbols. These are the things that we actually do see. So these are the words that we observe. So dog, play, the. Any word that you observe in a sentence, these are the terminal symbols. And then we also have a set of productions that relate the non-terminals and the terminals. And so a production is defined as something as a left-hand side and a right-hand side. So the left-hand side always has a non-terminal, and the right-hand side has any collection of terminals and non-terminals. So you can go from non-terminal to non-terminal, or you can go from non-terminal to terminal, but you can't go from terminal to non-terminal. And then finally we have the start symbol anoints one of these special non-terminal symbols as the thing that defines what makes a grammatical sentence. And we'll see why this is important in a second. And this context-free grammar formalization is pretty flexible. So you can have unary rules that attach some sort of syntactic structure to individual terminals. And this could be something like part of speech tags. We can also mix terminals and non-terminals on the right-hand side so that you can have lexicalized expressions or sort of fill-in-the-blank style rules in your productions if you want to. And you can also have empty terminals. So if you have optional components in a syntactic rule, you can express that using an empty terminal expression. The next thing that we'll talk about is derivations. A derivation is a sequence of steps that take you from your start symbol to a final sentence. At each derivational step, you replace one of the non-terminals in your current structure with some rule. So you take the left-hand side of a rule, you replace that left-hand side with the things on the right-hand side of the rule. So let's see an example of this. We have some grammar defined by a bunch of productions. And then we have our derivations, and the first derivation, S1, is just the start symbol. And we replace the start symbol with some rule from our grammar. Now we can replace the NP in this derivation, and we can then replace the det, and then the noun, and then we can start replacing the verb phrase within a single verb, and then a terminal. And so now we have, in our derivation, only terminals. And so this means our derivation is complete. We can't go any further. And so this is how you go from an empty parse tree to a complete sentence. So now let's talk about some terminology. One important concept that we'll need is that of a yield. And so the yield of a parse tree is simply the terminals produced by that parse tree. And the yield is all that we observe. What we actually want to do in practice, however, is given a grammar and a yield, we want to determine the set of possible parse trees that could have produced that sequence of terminals. And we'll call this the set Tg of S. How do we go from this collection of terminals to this set Tg? And often, this set has more than one element. So if the TG set has no elements, then the sentence is not grammatical. If it has a non-zero number of elements, the sentence is grammatical. There is some derivation in the grammar that produces that yield. What's interesting is the case where you have more than one possible parse tree that could have produced your yield. So if you take the sentence, the man saw the dog with the telescope, under some grammar, there could be two different parses that produce that sentence. And so this encodes the ambiguity of what is the phrase "with the telescope" modifying. So in this case, we see that "with the telescope" is part of a prepositional phrase, PP, and it has some internal structure. And the ambiguity comes in as to whether that phrase is part of a noun phrase or a verb phrase. Both are permissible. A verb phrase can have a prepositional phrase, as can a noun phrase. The grammar allows both. If it is part of the noun phrase that includes the dog, it's talking about a dog with the telescope. So maybe a dog has a telescope strapped to his back. On the other hand, if "with the telescope" is part of the verb phrase, then this means that it's modifying the word "saw." So the manner in which the dog is seen is with the telescope, and this is the more likely interpretation. But how do we formalize that preference? If the grammar allows both of them, how do we know which to prefer? And the way to do that, as you can probably guess, is that we want to attach probabilities to these two derivations. And so we'll do this by adding a notion of probability to our context-free grammar. And that's what we'll be talking about for the rest of today. So what we want to do is, instead of just having a set TG given a particular yield, we want to have a distribution over the possible parse trees. So this leads to a couple of questions. One, how do we parameterize our grammar to give us this distribution? How do we learn this parameterization from data? And finally, how do we figure out the possible parse trees given a particular yield of a sentence? To parameterize a probabilistic context-free grammar, what we're going to do is assume that for every production, we have some function Q that tells us the conditional likelihood of having that derivation. So we're going to condition on the left-hand side, and then we're going to ask, what is the probability that that left-hand side turns into the right-hand side? So that's the probability of a particular rule, and then for an entire tree that has a bunch of productions, the probability of the whole tree is just the product of all of the productions that went into that tree. Now, of course, this doesn't sum to 1, so we need to normalize this, but that's a relatively straightforward process. So how do you estimate a probabilistic context-free grammar from data? Typically, the answer is to get a bunch of sentences and parse them. And most famously, this was done by Mitch Marcus, who parsed 1 million sentences from the Wall Street Journal. And this requires fairly sophisticated annotators, so for example, linguistics grad students. But once you have a bunch of parse trees, it becomes fairly easy to compute the conditional probability of a rule. So if you want the conditional probability of a noun phrase turning into determiner adjective noun, then all you do is take the MLE estimate of the number of times you saw the derivation in P goes to det adjective in N, and then divide that by the total number of times you ever saw in P as the head of a rule. You'll notice that we're taking the MLE estimate. Why don't we do smoothing here? One reason that you might not want to do smoothing is that not doing smoothing rules out a lot of possible trees. And so you get fewer options of grammatical sentences. And as long as your grammar isn't too fine, you'll still get all of the grammatical sentences. It's not to say people never do smoothing, but it isn't as important here so long as you don't have too fine a grammar. Algorithmically, we're going to do something very similar to what we did for the dependency parses. And eventually we'll get to the notion of probabilities, but first we'll just consider the question of whether a sentence is grammatical or not. And to do this, we'll build up a chart with all of the possible derivations of given spans, and then we'll just check to see whether there is a derivation that covers the entire sentence, and that will tell us whether the sentence is grammatical or not. What we're taking a look at is something called the CYK algorithm. This is named for Cook-Younger-Kasami. And what this does is it assumes that you're given as input a binary grammar and no recursive rules. That is, you don't have the same non-terminal on both the left-hand side and the right-hand side of a rule. You have an input of a grammar and a yield, and you begin by initializing an array of booleans, and you set all of them to false. That is to say that a priori, no possible span is grammatical. And this array has three parameters. You have the start of a span, you have the end of the span, and then you have a non-terminal. This is saying, for the span, starting at S, ending at T, is there a non-terminal in that explains the yield in this span? And now, what we're going to do is we're going to first look at singleton derivations. So we take a look at each individual word in our yield, and we see, is there a production that explains that word? So this is equivalent to looking for individual rules that explain single words. Now we need to consider spans of increasing length L. These spans start at position S and have length L. They also have an associated pivot position K, and this pivot position tells us where this larger span is broken up into two subspans. So what we're trying to do is we're checking for every rule in our grammar that takes a left-hand side alpha and produces a right-hand side beta and gamma, where we switch from beta to gamma. This is called the pivot position. So what we do is we first check whether the non-terminal alpha is already associated with this larger span. If it is, our job is done. Otherwise, we then need to see if we can break up this larger span into two subspans. This is the dynamic programming step. So we check to see if we've already figured out that there is a span associated with beta and gamma that goes from, in the case of beta, from position S to S plus K minus 1, and for gamma, from S plus K to S plus L. And if both of those are grammatical spans associated with the non-terminals beta and gamma, then we say that we can have this longer span associated with alpha. So let's see an example of this. So we have a yield, book the flight through Houston. And here are some indices for the spans that we'll be using. So first, we look at individual words, and we build up all of the non-terminals that can be associated with those words. So most of these are unambiguous. There is only one non-terminal that can be associated with each of these words. Book, however, is more interesting. So it has two possible rules that can be associated with this word. And so we need to order our rules in a way such that we can look over these in order such that we can be sure that we won't miss anything. And this could go arbitrarily deep. And this is true for all of the positions, not just for book. Now we need to start looking at longer spans and put together shorter spans into these longer spans. So first we look at spans of length 2, and we can get a determiner phrase and a prepositional phrase. And so now we've gone through all the spans of length 2 and all the rules that could have put together spans of length 1 into spans of length 2, and now we look at longer spans. And so now we have a span of length 3 that puts together flight, the noun, and through Houston, the prepositional phrase. So to do this, this required us to have a pivot at position 3. The noun went from 2 to 3, and the prepositional phrase went to 3 to 5. So 3 was the pivot. That was the dividing line between those two subspans. And in considering this span, we also needed to consider other pivots. So for example, you might have had some combination of flight through as one subspan and Houston as its own singleton subspan. But there was nothing that was grammatical that fit those constraints, so it was not included. But we considered it. There's also a subspan of length 3 that combines a verb phrase and a determiner phrase into a sentence. At the very end, we're considering a subspan that's the entire length of the sentence, and there's only one derivation that explains the entire yield as a sentence, and this is book the flight through Houston, which considers book as a verb. And so we've now determined that we should not consider book as a noun in this context. By this point, it should be fairly clear that the complexity of this algorithm is proportional to both the size of the grammar, that is the number of possible productions there are, and it's also cubic in the length of the sentence. So n cubed times the size of the grammar. But we want more than whether a sentence is simply grammatical or not. We want to be able to decide which ambiguous parses we should prefer over others. And so this requires a simple tweak of the algorithm. Instead of just storing a Boolean variable, we now keep track of the maximum probability of a subspan. We also have to initialize the chart so that the uninitialized spans have a 0 probability. And now we parse the sentence as before, and we take a look at the entry associated with the start symbol at the top of the chart, and that gives us the parse tree with highest overall probability given the yield. And like before, we need to have back pointers so that we can recover the actual parse of the sentence. Recap for today, we talked about a hierarchical syntax model called a context-free grammar. We extended that with a probabilistic interpretation so that you could learn to solve the problems of ambiguity. And in class, we'll work through some examples of parsing a sentence using a PCFG, and we'll discuss some morphology homework results.